So there are problems with the previous approach of allocating the space or the memory space to the processes, which can create external fragmentation, internal fragmentation. External fragmentation is the size of the whole which is left, and internal fragmentation is if we convert and allocate the blocks to each process. Let us suppose if the block size is 3 kilobytes and your program size is 10 KB, then it will be allocated four blocks, and inside the fourth block there would be unused memory, and that could be that is called, this memory is called internal fragmentation. So unused memory inside a block which is allocated to a process is called internal fragmentation, because this cannot be allocated to any other process. So that there are two problems, internal and external fragmentation. And this happens because we want to allocate contiguous space inside the memory to each and every process. So this would be process 1, process 2, process 3, because the memory space allocated to the process is contiguous. So we cannot allocate this to any smaller size section. So that makes a problem for us. And this could be resolved by help of paging. Now, what is paging? So paging is a process of splitting our program into a smaller section. So how that is done, we are going to discuss about it. So what is done, we divide the logical space, the logical program into pages, and we divide the same size the physical memory into frames. So what we do is we have a process P1, it will be divided into number of pages. Let us suppose n pages of some size. Let us suppose 2 KB. What I do is I divide my program into number of pages, and those pages would be stored onto non-contiguous spaces on memory into frames. So this would be stored into frames. Frames are also of 2 KB size, the same size as of the page. So the logical page size is being mapped to a frame on physical size. So this is one concept. Now how that mapping is done, that we will see. So what we do is we divide the physical memory into fixed size blocks called frames. The size is of power 2 between 112 bytes to 6 MB, and we divide the logical memory into blocks of same size called pages. So these frames and pages are of both of same size. We divide our physical memory into frames, and we divide our processes into pages. So whenever a process enters into the ready queue, it always declare based on the page size of the operating system which is managed. It will split itself into different number of pages, and it says, okay, I need these many 16 pages, I need 100 pages, I need 1000 pages. So that's how the process would be divided into. And from that number of pages, we know that how many frames are needed for that particular process. So when a process is executed, its pages are loaded into the available memory frame from the source, and backing store, the secondary memory, is also split into the fixed size blocks. Remember this saying, they are also same size as of the memory frame. So frame is similar to what is onto the secondary memory. So that is also divided into smaller sections. We have pages, then we have frames, and onto secondary memory we call them blocks, and they are also fixed size blocks. Run a program, n pages need to find n free frames. So this is how it is executed. Now what we did is, rather than having a complete program on a contiguous space, what we did is we divided that into smaller chunks, and the size of the logical address is same as of what is on the physical address. On physical address we call that frame, and in logical address we call that as a page. But all this would remove the problem of paging removes the problem of external fragmentation, but it still suffers with internal fragmentation that we will shortly see. Now, address translation scheme, how the address of a logical space page is converted into a physical frame number. So for that, first we need to look at what is generated by CPU. What CPU generates? CPU generates whenever it generates an address, because it generates an address to fetch the instruction, to fetch the data from the main memory. So it splits into two parts. One is a page number, another is page offset. So remember, this total is the size of the logical addressing scheme. This is the total size of 2 raised to power n. M is the size of logical addressing. Why the memory inside the inside computer is always represented as power of 2? Because it's binary. So a 1 wire would carry 1 or 0, so 2 levels. 2 wires would carry 4 levels. 3 could carry 8, and this could carry 16. So every wire could carry 1 1 0 1 0 1 0 1 0. So when they are combined, the least significant bit and the most significant bit creates 2 raised to power 4 levels. So that's why everything what we do inside computer is always the power of 2. The logical address space. So when we say the logical address space, so these 4 wires could actually identify 16 locations from 0 to 15. So these 4 wires can identify 16 addresses uniquely. That's why the address space is written like this. So M would be the size. Now the logical address space is to the power M, and this is divided into M minus N is a page number, and page offset is D, is N. So just remember it. I'll come back to this. So this is a diagram of paging hardware, how the paging is maintained. CPU generates page number, and it generates D, the offset. Page number is used to look at page table. Now this is, remember this thing, this is per process page table. Remember this. This is important. We are going to focus on page table only now. So what is page table? Page table contains the entries for each and every page that is inside the logical address space of the process. So process enters, it says I have 10 pages. I need 10 pages to be executed. So it requires 10 pages because each page would have some size, and it requires 10 pages. So now what would happen? 0, 1, 2, 3, 4, so on, 9. So this is P. This P is the index of the page. So page number, which page number it wants. Now CPU would give me the offset. This P is equal to the page index because it is managed per process. This page table only includes the entries for that particular process. Remember, so each and every process would have its own page table. So P is holding and indexing which page number I want to search. Then this page number would hold the address, the actual physical address of what is here. So frame number here. So frame address would be captured here. So it will be capturing the frame number. So what would be stored here? Some frame number. Okay. And that frame number would be generated and added to offset. Now this D is just given and added to offset. So this combination would generate our actual address. Now this is something similar to what we did in the previous. We have base register and we have limit register. And based on that, the combination of both, we were able to access each and every memory. Now what we did, this particular thing splits the logical addressing from the physical addressing. So the translation is done here. So the logical address is created by CPU. It is translated here and here, and then the physical addresses, actual physical address is happening here. So we are able to distinguish between logical addressing as well as the physical addressing. So there is a mapping happening. With that, the programmer need not to think about where to actually store the program. It would be done automatically, independently. The programmer has need to just write down his or her program, and then the whole of the mapping and management would be done by the the hardware or memory management unit. Basically, it takes away the responsibility of doing the memory management from the developer. He or she can just focus on writing the code rather than concerning about how it would be stored and fetched by the CPU. So, number one. Okay, so paging is done by extract the page number, use it to index the page table, extract the corresponding frame number from the page table, and replace the page number in the logical address with frame number and add it to the offset. That would generate our the physical address. So page number, the size of the page. Now coming to offset thing, what would be the offset? How you would say, okay, if I say, if this generates 0, it will go to the 0th page. This would give the base address of this frame. Now this is what? This is a frame. Now this is holding the starting address of the frame. So whenever a page 0 is given, it would give us some frame number and it will give us the address of that frame, the base address of that frame. Now, as we know that the frame size is same as of the logical the page size. So page size is equal to frame size. Okay, so now page 0 and this offset. Now this offset would be used to reach the memory location inside this particular. So this offset D would be giving me the location where I need to reach. I think this is clear. Now page size is defined by the hardware. The size of the page is the power of 2, typically varying between 4 KB to 1 GB per page, depending upon the computer architecture size. So if the logical address is 2M, the page size is to the power n, then the higher order m minus n bits are logical designate the page number and the lower designate the page offset. Now this will be clear here. Now this is my logical view, logical address space. So my process requires 4 pages. Now page 0, and this is page table related to process. Now if I want to access page 0, I reach here, page table. Now this is the number of the frame. So number frame 1 is holding my page 0. I reach here. If I want to fetch some content from page 1, I go to the index 1 where the frame is stored at, this is stored at 4. My page is stored at, the page 2 is stored at 3. My page 3 is stored at 7. What happens here? Now you can see our physical memory space has been divided into frames. Now the memory is not contiguous here. So what it helps in? It helps in removing the issue of contiguous space requirement. Now what is offset? Offset is given by D, and that is some address within that page size. Now this page size is, let us suppose, of 2 KB. Okay. Now what would be D? D is equals to 2 raised to power n. So when it is 2 raised to power n, what it means that, so let us suppose I'm reaching here on page 0, 0th location here. I want to access anything from this particular page using these offset bits. So these are offset bits here. So if I say it is 2 KB, how many bits are needed for it? 2 raised to power, what would be the n? Let us suppose everything is 1 by 2 raised to power 11, because 2 raised to power 10 is 1024 bytes. 2 raised to power 11 is 2048. Yeah. So now the offset is basically the page size is 2 KB. Now within this location, let me draw it again. This is my frame size. Frame, and here is location 0, and here is location, let us suppose is this is my frame size. For accessing this memory, how many bits I need? 11. Using these 11 bits, I can access anything in between it. So I can access any location in between this frame. Okay, so these 11 bits become my offset bits, and the first n minus m minus n become my page number. Coming back here, so now page offset is the size of the page. How many bits are needed? So what would be n? It would come from page size. If my page size is 2 KB, then N would be 11 here. And rest would be from M, the rest would be our page number. So if it is 2 raised to power M is a total, then M minus 11 would be the bits used for page number, and this total 2 raised to power M would create a logical address. This is what is address generated by logical address. The logical address, which has number of bits equals to 2 raised to power M minus N into 2 raised to power N, which is equals to 2 raised to power M. So this is the logical address space size, which needs M bits to access any location from the process. Now what is this? We know the size of the logical address space, which is 2 raised to power 16. We know the page size, it is 2 raised to power 11, which is offset now. And what would be the page number? The page number, how many pages could be there? And the page in that page table, 2 raised to power 16 minus 11 is equals to 2 raised to power 5. So it is 32. So there would be, this would be from 0 to 31. So these many pages would be there inside the page table. Okay. So it will be clear as we move forward. Okay. Now what we discussed here is that every page is converted into some frame number, and then D is added. D is added here. D is an offset. D is an offset used to access any location inside the. So first we reach the base address, and then using D, we reach the exact location. Let us suppose now this would also make more sense to you. So here the logical address is N is equals to 2 and M is equals to 4. Now using the page size of 4 byte, a physical address of 32 bit, the logical address space 0 offset 0. So here let me do that. So I want to reach from 0 location to the this is a logical address, 0th location. So how it is done? Now first thing is page number. Page number, I go here, and the offset here is page number is 0, and it is stored at frame 5. So I go to frame 5, 0, 1, 2, 3, 4, 5. So it is here. I reach here, and I added the offset. What is offset? 0. So I reach this particular point. So A stored here goes to A on this particular location. Now I want to retrieve the logical address. So the logical address 0 is mapped to physical address of 20, where M is the frame size, because each frame size is of 4 bytes. So 5 into 4 plus offset it is 20. So this location is 20th location. Okay. Now let us suppose the logical address 3. Logical address 3. Let's see where it goes. Logical address 3. Because this is from page 1, page 0. So I'll go here. Now from here, I'll reach here, this frame, and then offset the value. So it is 5 into 4 plus 3. So what it is? 23. So the memory location 23 is used to store the fourth element, the location address, logical address 3 into 23rd location. So this is how it is done. Now logical address of page 4 in page, the logical address this, where it goes, frame 6. Frame 6 is here. I reached here. And what is offset here? Offset is 0. So I reached here. So what it is? 6 into 4 plus 0. It is equal to 24. So my E in the logical address space is written on to 24th memory location in physical address. How to calculate the internal fragmentation? Let us suppose the page size is of 2 KB and the process size is this much. So how many number of pages are needed? So obviously process size divided by page size would give us, if it is in fraction, it means that we need an extra page. So 35 pages plus these many bytes are extra. So for this, we need to add an extra page to it. So 36 pages would be allocated to this. Now in the last page, because this is a size, this minus this, these many bytes are empty, non-used. and this is the size of internal fragmentation. So what is done? We can reduce internal fragmentation by having small size frames. It would be better if we have small size frames, because smaller the size, lesser would be the unused space. Okay, so now this is also important. Frequently, 32-bit CPU, each page table entry would be 4 byte long. Now we have a page table, and each entry, this entry is of 4 bytes long, but can vary. The 32-bit entry point can have 32 physical address frames. So if it is 32-bit, if my address space is, let us suppose, what I mean to say is, let us suppose the logical address space is like this. If my logical address space is like this, so how many size of the memory is needed? It is basically 2 raised to power 44. So if 32-bit entry points to 32, because each entry is of 32-bit, okay? It means that it is pointing toward 32-bit. Now this is page table. Now each page, this is holding 2 raised to power 32 entries. This page is table. Let us suppose this is holding these many entries. Okay. So if this is this, and then we have an offset of 12 bits, then what would be the size of physical memory? It would be 2 raised to power 44, because this is one entry for if this is a page table, it points to the start of a frame. If this is a page table, points to the start of the frame. So if this includes 2 raised to power 32 entries, where each frame size is 2 raised to power 12, then what would be the size of this memory? It is 2 raised to power 32 plus 12, it is 2 raised to power 44, and which makes it equal to 16 terabytes of physical memory. What I mean to say is that the physical size and the memory size could be of different, different. The logical address space and the physical memory size could differ based on how many entries are there and what is the size of the page table. So that based on that, this would differ. So this is what I wanted to say here. Okay. So now easiest is, let us suppose a process enters into the ready queue. It will announce its pages: page 0, page 1, page 2, page 3. So it requires 4 pages now. Then the operating system would be managing a free frame list. So what is done? Page 1 is first stored onto the memory, and then once it is stored into the memory, an entry has to be made into the page table. So page table would be created. So page 0 stored into frame number 14. Then another page is taken, entered into the page table. Then this page table is allocated a location of frame 13. So this entry is done. Page 2 and page 3. So similarly, all pages whichever are required by the process would be entered into new page table, and based on this we can perform the mapping of logical address space to the physical address space. What happens is we implement the page table based on page table. Page table is per process information table, so it used to capture the information which is there for each page table. This is important, please try to grasp it. So for each process, there is a page table, and CPU would generate some address, and based on that address, the page number is, it will find out the frame number that would be added to the offset D, and based on frame number plus D, our location is done. Now, there could be one question based on this number of bits and bytes. So that's what I was actually trying to tell you, because you need to be very clear on that the logical address space is of 2 raised to power m. Then we have D is equals to 2 raised to power n, and m minus n, 2 raised to power m minus 1 is used for this. So whenever we have 2 raised to power m minus n entries into page table, each entry is basically starting at the frame number, and those frame numbers are physical locations. So this is how we move from logical address space to physical address space. Number one, what we concluded out of it is that there is no external fragmentation now. Number two, we talked about there is still internal fragmentation using paging. Number three is that the logical address space is different from the physical address space. Mapping is performed based on the page table. So page table is very important, which is created for each and every process. So we talked about PCB. Whenever we say PCB, this includes the page table also. So this will hold the page table for that process also. So whenever a context switching is performed, the page table would also be context switched. Okay. What happens is whenever a process is happening, so a logical address space, how the access is done, CPU would generate a logical address space. Now, logical address first checks this memory, the page table, in a normal process. What was happening here? What was happening? This generates a logical address. This would access this address space. Then using this, actual address space would be monitored. So for generating or fetching the actual information, we need to access two memory locations. We need to access two memory locations, number one and number two. So this is what is being accessed. Now for that, for making it little easy and fast, a TLB is used. It is an associative memory. Now what is associative memory? It's a fast memory which can perform sequential access. So it is the parallel access. So whenever a page number is done, it is not indexing like first, second, third, fourth, fifth, sixth. It's not like that we do in linked list. It is just sharing the same page and with everyone at same time. This is hardware based. This is hardware. This is not software based. So this is hardware, and this is associative memory, which associate the contents with what is needed. So for simplistic sake, the TLB is able to fetch in parallel whenever there is information available. So it will search the same page in all the different locations at the same time. So what is the process of TLB? It is a parallel memory which can access all the location at same time. We need not to perform sequential access. So that makes our process faster. So if we get the page number here, it would actually generate a frame, and that frame is used to physical address. Now, what is the benefit of this? This would reduce the memory access time. Why? Because we are not indexing into page table, but we are just looking into the TLB, which is faster and not doing sequential, goes in parallel, generates instantly the page number, and from there we can generate the physical address. Initially, this was not there into our plan. So the only thing was CPU generates logical address. This goes to P. This is a memory thing, and this has to be sequentially because it's an index. So we go by indexing, we search by indexing. So it is just like traversing. Okay, so we traverse to find out whenever there is a page number, similar page number match is found. So this is just like for loop or while loop. We go over and then search this table. This will take time because what we are doing is this address has to directly reach here, but it is first checking this and then accessing the memory location here. That increases the time. That increases the time to find out the actual data. So in place of that, what is done? A special hardware is used, which is a memory, associative memory, which can search all the location in parallel. In single go, it will search all the locations which are there for that. It is a hardware, so it can search all the locations and generate the frame number. So it is much faster than this. So in that case, what would happen? We can consider that it is considerably taking no time. So if this is done, we got the frame number. So actual access would be just one hit. So we got the frame number and this would be captured. So this would generate only a single memory access time. So MA is memory access time. But if we are not using TLB, we have two memory access time. Like one memory access is here another memory access is here, so it was double. So to reduce that, TLB is used, and that would generate a memory address or whatever we want to fetch in single memory access. Now, because this is costly and would have limited size, so what is done, only kept smaller section of the program here, smaller number of page entries here into TLB. So what is TLB hit? If we get page number, frame number for a page number in TLB, then it is called TLB hit. If we did not get the page number in here, then what is done, the normal procedure is followed. So for that, we come back to the page table, access it, and then we go to the memory access. So whenever there is a hit, we have a time of 1 memory access. Whenever there is a miss, it would take this time of 2 memory access. Now let me, so hit ratio. Hit ratio is a percentage of the time the page is found in associative registers. Let us suppose the hit ratio is 80%. I mean to say, now 80% is the time that we find information in TLB, and it takes around 20 nanosecond of TLB search and 100 nanosecond for memory access. Now, in this case, what would be the estimated access time? 80%, 80% of time it is in the TLB search. So we just say this is 80% is TLB, so 100 plus 0.20 into 200 is equals to 120. So I think 200 is the total time when we are doing, because 100 is a memory access. So we are not considering this part here. Let us suppose. So 100 is 100 nanosecond is 1 memory access time. So whenever 80% time we would have 1 memory access time, and 20% of time we would have 2 into 1 memory access time. So it will be 80.80 into 100 plus 0.20 into 200. It will make average expected access time of 120. So rather than always taking 200 nanosecond with TLB search, we are able to find this thing in 120 nanosecond. The effective access time reduced to this. Now, if our hit ratio becomes 99%, and in that case, our estimated time would be 0.99 into 100 plus 0.01 into 200. It becomes 101 nanosecond, which is approximately 100 nanosecond. So if we are able to generate a TLB or use a bigger, larger TLB size, then our memory access would only be of 100 nanosecond, which is equal to 1 memory access. Yeah, so if we are looking here, one memory access time would be used here to search, and then one memory access time is used to search here. So if memory access time is 100, so 100 nanosecond would be used here, 100 nanosecond would be used here. If we are not using TLB, then for each entry, 100 nanosecond would happen here, 100 nanosecond would happen here. In case we find for 99% time, we find a page frame here. So it is not going to take any time. It's very small. It's not going to take any time. So 99% time hit is happening. So for 9900 time, 99% time, access time would be just equal to 1 memory access. And for the 0.01 time, this would take this route, because now this is a TLB miss. So this would actually take this route, and it will take 100 plus 100 is equal to 200. So that's what is mentioned here. So 0.80 into 100, 1 memory access time, because whenever TLB hit is there, it will take time equal to 1 memory access. So that 100 is coming here. 80% time this 100 nanosecond, and 20% time 200 nanoseconds. So now this 200 is 100 plus 100. So this makes my time equal to average estimate time for 100 times. So if we are doing some search, the average time would be 120 nanosecond. Now, if we increase the hit ratio, how the hit ratio would be increased? If we increase the size of TLB, like whole of the page table is into our TLB, then let's suppose we have 99% we match. Okay, so in that case, our estimated time would be 101. Let us suppose my alpha is 100%. TLB hit is 100%. What would be the estimated access time then? Exactly. So it will be 100 nanosecond. There would be nothing for the miss. Everything would be found. Let us suppose our alpha is 0. Alpha is 0 means it is never found in TLB. Always a miss. Page number is never found in TLB. Then what would be the average time? It will be 0 into 100 plus 1 into 200. So it will be 200 nanosecond. This is the case when alpha is 0, always a miss. And the other one was the case if this is 100, then it means the TLB is always hit and everything would be of 100 nanoseconds. Memory protection. Now, what is memory protection? I told you earlier that there are different processes those are running. Each process would have some memory location, memory space. And we don't want that process P1 access here, process P2 accesses here, process P3 accesses the other space. That is one memory protection. Now another is, this is done by using valid or invalid bit attached to each entry. Now because we want the frames and we have the frames, and the frames could be valid or invalid in the page table also. Okay, this is important. Please focus on this. What is valid and invalid bit inside the page entry? So valid indicates that the associated page is a process is in the process logical address space and thus a legal page. What we are going to do, we are going to attach a bit. Now invalid indicates that the page is not in the process and not in the process logical address space. So what we did is, inside the page table, we add in valid or invalid bit. Valid invalid bit, what it says, now you can see page 0 has entry till page 5. So there the page table size was bigger. We say page number 0, 7, these are just pointing toward give me one minute. These are pointing toward the frame numbers, but they are not valid. So using valid or invalid bit, we can say we protected the frame, the location which a process cannot take away. So if there is any access to this frame, this bit would be checked, and based on this, no access would be provided to any of the frames on the physical memory. So this valid invalid bit is used to provide the protection. Just keep in back of your mind, we'll come back to this. Now, as we know that the pages, the frames are stored like this. They are non-contiguous. They are stored like this. Now, for each and every frame, there is an entry into the page table, and from the page table, we can actually fetch the logical address whenever it is accessed. So what could happen if my library is there, which is shareable, libc, usually used by every program on Linux. So most of like programs would be using libc. So what is done? So for that, let us suppose there are 3 processes, P1, P2, and P3. As I told you, this is page table is per process. So every process would have its own page table. Each one is accessing the libc. Each one would be trying to access the libc file, libc library file. How it is split? Now libc file, it requires, so it is split into number of pages. One thing is done. Created pages, page 1, page 2, page 3, page 4. Now then it created the page table entry. So for frames, this is at third, this is the page entry. Now this is how it is saved. Let us suppose this is coming here, this is coming here, this is going here, and this is where it is for P is at 4 here. Okay, now other processes are also using the same library because the logical address is separated from the physical address. We could use, now this is physical address, the physical memory. We could utilize and share this with multiple processes. How? because this is also accessing. Now here we just need to put this frame. Where is lib1c? It is located here. So this is located here, this is located here, and this is located somewhere here. So what we did, because of this page table entry, we are able to separate the logical address space from the physical address space, and that enable us to have shared code. That's how the shared libraries are being used. If you remember, we talk about dynamic linkable libraries. So they are mostly shareable libraries. So they are loaded, and each process which wants to use them, they would just be pointing to the same frame. So now the problem here is that multiple processes are accessing the same location. And we have discussed this, how this is handled. When all are just reading, so they are fine if all are reading, because mostly these are re-entrant code. Now here I use a read only. This is called re-entrant code. So re-entrant code is read only. So whenever it is read only, multiple processes can share this code and work on it. This would decrease the size of the total program used. Now moving toward the structure of the page table. How we want to structure the page table. Because what we did is we have one library, system library, we stored into the physical location, because that is being accessed by multiple processes. So in the page table entry, all different processes would hold the same frame number, because that is a read-only code. So there is no harm in allowing multiple processes to read the same code. And this is possible because we split the logical view of the program from the physical view. Because from the programmer's perspective, its program is actually using the library libc independent to any other process. This is using libc independent of any other. This is using independent of any other. So if we have a fixed location for each and every process, then we need to keep 3 different copies of libc inside the main memory. And these libraries are large in size because there are so many implementations, so they will take whole RAM as is. And this functionality of splitting logical view from the physical view enables the sharing of the memories. The important thing here is that you should be able to visualize in your brain that the logical address space is the one which programmers see, and the physical address space is the one which is actually stored. Now, how that mapping is being done? One, we discussed about base limit registered. Now that was good for when we have contiguous spaces for the processes. When we had contiguous process spaces, then the problem of external fragmentation was there. To remove that, we come to paging, which divide the whole process into smaller page sizes, and the physical memory into small frame size. Now frame size is equal to the page size. Then we changed our mapping mechanism. The mapping mechanism is changed from base and limit to the page table. Now page table is private to each and every process. It holds the page for a given page index. It represents the frame index, and offset is used to fetch the actual location. This divides the logical space from the physical space, and this enables us to share the code within multiple processes. Okay, now coming to the structure of the page table. What would be the structure? What could be the size and how it could be handled? Just listen it like if this is the logical address space, 32-bit logical address space. What does it mean? So 32 logical address space, it means that we have to find out M and we have to find out N. So what is M, N minus M? And what is N? N is page size, which is dependent upon hardware. So we know that based on hardware, we know the page size. Page size, we now the page size we have taken 4 KB. What does it mean? 2 raised to power 12. So n here is 12. What is m minus n? 2 raised to power 20 into 2 raised to power 12. So this was the page size. And now what is this? What is this? 2 raised to power 20. This is size of your page table. Page table. So consider the logical rest space is 32-bit. Page size is of 4 KB. Then the page table would be having size is equals to 2 raised to power 20, which is 1 million entries. The page table would have 1 million entries, and let us suppose each entry is of 4 bytes. Whatever is we are storing, this is a memory because it is going to store some address space. So it is of 4 bytes, and then the table size would be of 4 MB. Do you think it's big or no? 4 MB. So each process would have a 4 MB size of page table. Do you think it's big or no? If you write a code, just look at the longest code you have written. It would be in KBs only. It will be 1 or less than that. So 1 KB, 10 KB, just like that. So your longest code, whatever is, that is in KBs. Now for running this code, you need 4 MB of the page table only. And this is huge. And this would actually increase the size of PCB. Okay. So when the PCB size increases, it means the context switching would be slow and whole system performance would go down. So that amount of memory is going to cost us a lot. So what can be done? We have hierarchical paging, hashed page tables, or inverted page tables. I just want to go little quickly. So what we can do is break up the logical address space into multiple page tables. So rather than having one page table, we could have multiple page tables. So page table number 1, page table number 2. So if the entry is here, otherwise the next entries would be here, and so on into next page table. So what is done? Let us suppose this is an outer page table, and then we divide it into internal page tables also. We split it, smaller page tables. So based on this, we could access the similar memory space. So how it is done? Let me go to the exact. Okay, now this is better. So the logical rest space of 32-bit, the page number consists of 22 with the here the page size is 1 KB. So page offsets is 10-bit. The page number is of 22. So what we do, rather than having one page table, we split this addressing scheme into 2 page tables. So P1 with 12 bits and P2 with 10 bits, and then offset is of 10 bits. So because here the page size is 1 KB, and P1 indexes into the outer page table, P2 indexes into the displacement within the page of inner page table, and this is known as forward mapping. So this is how it will map matched. So there are multiple, basically again now pages here. So within that, what we do is page number entry this would point to some page table in P2, and this P2 would reference the location. P2 is number of bits. So here it is 10. Here P1 is 12-bit, this is 10-bit, and this is 10-bit. So this is 12, 10, and 10. So make 32-bit logical rest space. Okay. So what is done? Rather than having, as we discussed previously, so 4 MB is a large size to be kept. So large memory space is taken. So what is done? We, rather than splitting and just keeping one page table, the pages are 2-level paging is done. Let us suppose 2-level paging is done. So page 1 and then page 2. So in that case, this would actually reduce the page size of individual page size. So would be having smaller pages rather than one big page, and all entries in the page table are never required, as we have seen valid, invalid. So these inner pages, all pages would never be required. There would be smaller entries, those would be required. So for that, this P1, 12 bits would just be doing the calculation for the 12 most significant bits, and within that, for each 12 bit, another this would create some location and check for the next 12 bits. So this would actually enable and find out the location here, and this is the final value which would be giving us the frame address. So this come back here. So outer page table would just be selecting this outer page table, we just be selecting the entries here, just what we do for the physical memory mapping and the logical address space. So these 12 bits would just be selecting smaller chunks of page of page tables. This would be selecting page of page tables. So there would be these many pages, smaller pages, which each with 2 raised to power 10 entries. So each would be of 1 KB size. So that would create a smaller chunks. Now what I told is not every page is required. Not every page is required. So there would be smaller number of pages. Those are needed with this mechanism, and we can handle it with the lower memory space. Now, another is the problem comes with if there is 64-bit logical address space. If this is 64-bit address space, then we could convert this into 42-bit inner pages of 10 and 12. This is still so big. So it is basically the outer page size would be 16 GB. Outer page size would still be 16 GB if our address space is 64-bit, and which is problematic again here. So what we can do here is we can split it into multi-level, 3-level. So rather than having just 2, we can divide this into 3 levels. So 30-bit, 32-bit, 10, 10, and then offset, or we can reduce it further, 22, this is 10, and so on. But that makes the system very, very complex. So we don't use that particular thing. Now comes the hash page tables. So hash page tables are basically using the hashing. So how it is done, it is more simplistic and easy to understand. So the logical address space would be given to an hash function. Hash function would create a hash value, and that hash value would be used to look into hash table. So hash value would look into hash table. If there is a conflicting, like more than 2 values have a same hash value, then there is a linked list maintained. Now that linked list, first value would be the page number, which is required, and this S is the frame number. So let us suppose page 0, the frame number 5. Based on this hash value, the page number would be matched, and that page number, if it is matched, then we give that to the same function, and based on offset R plus D is generating the physical address. I hope this is better. Let us suppose R is the page number that we are going to access. For this, hash function is created, hash value is done, we reach this location where we found the linked list, and we just compare with Q. R is not Q, so we move forward. Then we go reach, sorry, I have to give a P here. So if we reach Q is matched with P, it's not matched, we move forward. Now P is matched with P, so we got that. We are looking for this frame number, and what is returned now then? The frame number. Frame number is added to offset, and we got the physical address space. As you know, hashing. So hashing, this is simplistic, and the size is always constant. Now another is inverted page tables. So inverted indexing. What is inverted indexing? All of you study so many books. So at the end, normally there are topics given and their page number is given. So for this topic, you go to that particular page. One is table of contents. Another, at the back end of the book, there are some indexes given. Those are called inverted indexes. So we go by topic, not by page. We go by topic. So I search for the topic, and then I go to that page. Now, inverted page table, what happens and why it is used? Because let us suppose your processes may have thousands of pages needed. So, or as I told you, that not all pages would be required inside our program, not all pages would be valid. So in that case, the page table size is very big. This is what we have seen in previous two approaches. So in that case, rather than keeping the page table, what is done, whatever frame is allocated, whatever frame. So let us suppose there are few frames, those are allocated. So frame 1, let us suppose frame 2, frame 3. So only 3 frames are available inside memory for the pages. Rather than keeping the pages information, we can keep the frame information. So this whole information would come here. So the frame table would be matched. Now what is done? Only this table now would be capturing information only for those frames which are existing in the memory, not anything else. Rather than keeping the pages and then to mapping the frame, because frame would be smaller number than the pages, because all pages would not be required and not loaded into the memory. So the number of frames would be less. What is done? Rather than keeping the page index, there is a global page which keep the information of the frames in the memory, and we can search this based on the part. Now the logical address has changed here. So the logical address here is PID P plus D. So PID is the process ID. So we know that the process, which page number, and D. So based on this PID and P, this inverted page table architecture would generate the frame number which is available, because this page is global page, number 1, and number 2 is having information only related to the frames which are there inside the memory, and it relates like for PID this and page number this, where the frame is located. So it would be needed. So this is an architecture for that. This reduces the size of the page table. Okay, let me just reiterate what I said. As we discussed that the page table is important for our processes to do the mapping, but the page size is always a problem. So we discussed various mechanisms. One is hierarchical page tabling, other is hashing, and third is inverted page table. In hierarchical and hashing, hierarchical we split the bigger large size page into smaller pages. In hashing, we create the hash table to find out the frame number, and in inverted, what we do is rather than keeping the page information, we just keep the information about the frames, those are inside the memory. And for that, we need information of to retrieve the frame for a particular page. We need PID and P. Based on PID and P, we will find out this value I. I is a frame number, and this would be added to D to find and reach the location. Swapping is a process. Rather than keeping all the pages, all the frames into the main memory, we keep only fewer frames into the main memory, and that would enable us to free the RAM, and we could actually activate a large number of processes. So as we know, the multi-programming is the number of processes those can stay inside the RAM. With swapping, we can increase that multiple programming. Now how that is done? So you can see there is a process. So we can keep this process back to the secondary memory or backing store. Till the time it is inactive, it is not needed, we take it from the main memory and put back to the secondary memory. Whenever it is needed, we bring back to the main memory, and then we discuss. So we haven't discussed about long-term scheduler and short-term scheduler. Long-term scheduler would actually do this job. So which swaps from the main memory to back to the secondary storage. So swap out is putting back from main to the secondary. Swap in is putting back from the storage to the user space. There are two methods. One is standard swapping. We hold the process from the main memory to the storage, or from the storage to the main memory. So whole of the process, the complete file. of that process. It will take a large, switching time would be more because data transfer is more. The other approach is just paging. Whatever inverted page indexing works on, because of this swapping with pages. Only those pages are kept onto the main memory, which are needed, and all those which are not needed, page frames, those would be put back into the storage. With this, we could keep smaller number of frames related to one process into the main memory, and this would increase multi-programming because we have more free space with less frames per process. We can keep more processes into main memory, and we can perform better concurrency and CPU utilization because we have more processes into the main memory. So swapping with paging is moving just not the entire process, but a small number of pages. Those are needed for the process. So this will also reduce the size of the transfer of data and make the process very faster and efficient. Now, swapping is generally referred as standard swapping when we are moving whole process, and paging is referred as swapping with paging. So whenever we say paging, it means that it comes with swapping also, where all those frames which are not needed by the process currently would be put back into the secondary storage, and this is called page out and page in. The next chapter we are going to discuss would be focusing on demand paging, which is important, and how this is done. We will keep it from there. Thank you so much.